Dear friends, earlier in part 1, we have seen how to draw a project network diagram. Later in part 2, we have seen critical path method, how to find out the project completion time, and total float and free float for non-critical activities. For critical activities, the total float and free float will be 0. Now in part 3, we will see PERT, performance evaluation and review technique. Here we will see the requirement for drawing a network diagram, a case study on PERT, expected duration and variance of each activity, network diagram, earliest start time for all the events in the network diagram, latest completion time for all the events in the network diagram, critical path, expected project completion time, and finally the probability of completing the project in a given time period. Your project has many activities. Here is an activity diagram. One activity is shown. An event occurs before and after the end of an activity. You can see here tail event occurs before the start of the activity B. Head event occurs immediately after the completion of the activity B. Since your project has many activities, there will be many events, and all these events need to be completed in sequence as shown in the project network. The activity and predecessors, they are the two most important factors to be considered while drawing the network diagram. In this table, activity B, C, and G are shown. Activity A is predecessor to B. Activity A is also predecessor to C. Therefore, activity B and C will have a common starting event. See here, common starting node. Its event is called node. Now, activity G has got combined predecessors E and F. Therefore, E and EF are combined predecessors. Therefore, they will have a common ending event. So, E and F are combined predecessors to activity G here. This is very important. You should note down. In project evaluation and review technique, activity durations are probabilistic in nature. See the activity diagram here. 3 time durations will be given for this activity: optimistic time, most likely time, and pessimistic time. With this data, we can find out the expected duration and variance for all the activities. We will take a case study. Details of the project are given here. All the activities are given in column 1, activity A to activity J. The preceding relations are given in column 2. The time durations are given for all the activities: optimistic, most likely, and pessimistic time. What are we supposed to do now? First, construct a project network. Find the expected duration and variance of each activity. Find the critical path and expected project completion time. And finally, find the probability of completing the project in a given time period, 22 weeks given here. We will see all these things. First, we will take the activity A with the time durations. The activity diagram is shown here. The expected duration TE is given by the formula: optimistic time plus 4 times most likely time plus pessimistic time divided by 6 here. We will substitute these values. 5 plus 4 times 6, 24. 24 plus 5 is 29. Plus 7 is 36. 36 by 6 is 6. Similarly, variance we can find out. TP is 7. TO is 5, 7 minus 5 is 2, 2 by 6 is 1 by 3, 1 by 3 whole squared is 1 by 9. We'll put this expected duration along with the activity A here. Similarly, we'll find out the activity duration for all the activities. Now we'll draw the network diagram. For drawing the network diagram, we need these activity numbers and preceding relations. Okay, so activities are given as alphabets A, B, C, D up to J. And we see that from the table, A, B, C are having no predecessors, therefore they are starting activities. So we have completed this A, B, C activities easily. Now activity A is predecessor to D, therefore I will draw D here. So I have drawn this here. Now we'll see this. Activity B is predecessor to E. Activity B is shown here, predecessor to E. Similarly, activity C is predecessor to F. But E and F are combined predecessors to activity H. Therefore, they will have a common ending event. That's what I've drawn here. Then we will see here, C is also predecessor to G. So I will have to draw a activity G here. And E and F are predecessor to activity H. That's why I have to draw H here. But what happens, this H and G are combined predecessors to activity J. So E and EF being combined predecessors will end up in a common ending event. Now we will see here, D is a predecessor to I, therefore I will draw I, and G and H are predecessor to J, therefore I will draw J, and I and J are having no predecessors, therefore I will end up this activities with a unique head event, right? I and J are the end activities. They should not be dangling. So I have completed the network diagram. Only the duration I'll have to fill it up. For that I have to calculate the duration. We will see how to calculate the duration. Find the expected duration and variance of each activity. The formula is given here. T is equal to optimum time plus 4 times most likely time plus pessimistic time divided by 6. Variance is sigma squared is equal to pessimistic time minus optimistic time divided by 6, the whole square. I have the data available for all the activities. Simply I have to substitute and fill it up. I filled up. Expected duration and variance of each activity are obtained here using this formula. You can cross check later passing the video. Now I will have to find out the critical path and expected project completion time. For this, step number 1 is fill up the activity durations. We got the activity duration just now. I have copied it here. I'll fill it up now. 6 for activity A, 3 weeks for activity B, 4 weeks for activity C, 2 weeks for activity D, 3 weeks for activity E. I'll check it up here. 3 weeks for activity E is okay. 5 weeks for activity F, 3 weeks for activity G, 5 weeks for activity H, 5 weeks for activity I, and finally 3 weeks for activity J shown here. So I have completed all the activity durations in the network diagram. Now you'll have to find out earliest starting time for all the nodes. I've given an example here. For node 1, I'll have to take it as 0, and all other nodes will have to find out. See here, I will consider node number 6. Node number 6, there are 2 activities E and F. The earliest starting time for this previous node is 3. Here, for the previous node, it is 4. So I have to add the activity time. 3 plus 3 is 6. And for this, it is 4 plus 5 is 9. I have to take the maximum of these 2. Therefore, I have taken 9. Similarly, I will consider for all the nodes if there is a option. So see here, this earliest starting time for node 6 is 9 because 9 is the maximum of 6 and 9. Now I will fill it up E for all the nodes. Earliest starting time E for all the nodes. I'll start with 0 here, right? Then 0 plus 6 is 6. 0 plus 3 is 3 here. 0 plus 4 is 4 here. Then 6 plus 2 is 8 here. And here I have to take a decision. 3 plus 3 is 6. 4 plus 5 is 9. So maximum value I have to take 9. Similarly, here also I have to take 4 plus 3 is 7. 9 plus 5 is 14. So I will select 14 here. Then here 8 plus 5 is 13. 14 plus 3 is 17. Therefore, I select maximum 17 here. Now I will have to fill up the latest completion time L for all the nodes. For that, I have to start from the head event. Here I will have to take it as 17 and then backward pass. You will see that. I will give an example here how to calculate the latest completion time. I will take this node, 4th node here. There are 2 activities E and F and G here. So you will see here, this is 9. 9 minus 5 is 4 here. Here it is 14 minus 3 is 11 here. So I have to take the least one. 9 minus 5, 4 is the least one. Therefore, I have selected. Similarly, I will find out for all the nodes in the next slide. Here I have given the calculations for node 4. I'll take it as 17 here. 17 minus 5 is 12. We'll see it here. Before that, 17 minus 3 is 14. I have filled up here. 14 minus 5 is 9 here. I'll have to fill up 9 here. Then now I'll come here. 17 minus 5 is 12 here. Then 9 minus 5 is 4 here. Then here 9 minus 3 is 6. Here I have taken a decision because 9 minus 5 is 4 is lower than 14 minus 3, 11. Right? Here 12 minus 2 is 10. Again, we have to take an option here. 10 minus 6 is 4. 6 minus 3 is 3. And 4 minus 4 is 0. So the least value is 0. So I'll put 0. So we have now completed all the time E, earliest starting time, latest completion time in the network diagram. Now we will have to find out the critical path. Critical path is the longest path. The conditions for critical path is EI should be LI, EJ should be LJ. That is preceding node as well as succeeding node. The time should be same. For example, here this E value and L value are same. And succeeding node for this activity C, both are same, 4. And the difference between the L values 4 minus 0 and then E values 4 minus 0 is time duration for this activity. Likewise, we will find out here again 9 and 9, 4 and 4, 9 minus 4 is 5. 14, 9, 14 minus 9 is 5. Similarly here 17, 17, 14, 14, 17 minus 14 is 3. So You know this critical path is like here, C, F, H, and J. Adding the durations, activity durations, we find the total project time. So 4 plus 5, 9, 9 plus 5 is 14, 14 plus 3 is 17. We will see that here, the calculations. Critical path is CFHJ. We will fill up the mean durations, which we have calculated, variance, which we have calculated. We add it up, total duration will be obtained. So expected project completion time is critical path duration, which is X bar, we call it, is equal to 17 weeks. And critical path variance sigma squared is 4.78. The square root of that is standard deviation, 2.186 weeks. So now we will see how to find out the probability of completing the project in a given time period. Given time period is 22 weeks. So X bar is 17 weeks. Sigma squared is known. Therefore, sigma is 2.186 weeks. We have calculated in the previous slide these things. Now required completion period, X value is given as 22 weeks. We have to find out the probability that the time period will be less than or equal to 22. That is 17 is the mean time period for completion. We have taken 22 weeks. We'll have to find out this area to the left of 22. That gives the probability of completing the project in 22 weeks or less than that. So probability of X less than or equal to 22, we cannot find out from this table, from this distribution, because there is no table available, but there is a table available for standard normal distribution with mean 0 and standard deviation 1. Therefore, I will convert this X into Z variable. Z variable is used here. Z is equal to 2.28. We will see how it comes. X is converted into Z, X minus mu by sigma. It should be less than or equal to 22 minus mu is X bar, which is 17, divided by sigma is 2.19, 2.186. I have simplified into 2.19, which is 2.28. All I need to do is I'll have to find out the area to the left of 2.28, that is the value in this standard normal distribution curve. We can refer the table in any textbook, or we can use Excel formula in an Excel sheet. I will show it to you here now. When you do this, you will get this value of 0.988. We will see how to do this in the Excel sheet now. See here, what I will do is I'll put equal to NO or M. So I've got this on this. I'll put that, and 2.283, 2.283, comma 0 is the standard distribution mean, and 1 is the standard deviation of the normal standard deviation, and we want the area to the left. Therefore, I put true. I'll just put enter to get this value 0.988. If I want to get it in percentage, I'll put percentage here. This is there. So I want to have the added decimals, right? 98.88. Yeah. So what I will do is I will just go to this here. So 98.87 is the value here obtained here with the approximation, right? Now, so the area is 0.987. So 98.86% probability of completing the project in 22 weeks is the answer. This completes the PERT. I hope you like this video. If you like this video, please recommend to your friends. Also watch the part 4, the crashing of a project network. I'll stop sharing here. Thank you very much for being with me in this video. I'll stop sharing it now. You can subscribe also if you like it, so that you will get more videos.